All right, I'm going to go through kind of two big questions. The first one is given x and y as functions of time, and then I ask a bunch of questions. And then the backside is going to be looking at dx dt and dy dt as the given and kind of the questions we can answer. So this first part is kind of just, I'm just asking you to graph this just to give you an idea of the motion here. This isn't something that would be, on a Calc 2 or an AP test, and so y is some quadratic, and if it's, in our experience, we know that if this is a quadratic, the derivative is going to be linear and the second derivative is going to be a constant. So this has kind of constant positive acceleration in the y direction, so it's accelerating this way. And then the x is by a sine function. So that sine function is going to go up and down, up and down, up and down. If you think about what the graph of a sine function looks like, right, it's going to go like this. And so its horizontal motion is a sine function. So horizontally, it's going to go back and forth, back and forth. So it gets this oscillating back and forth. And you can see that the gaps get bigger and bigger and bigger because of the vertical acceleration, right? Horizontally, you're going back and forth in the same amount of time. So this is pi over 2, pi, 3 pi over 2, 2 pi, and so on, because this is a periodic function, right? It's got a period of 2 pi. But vertically, you're going to accelerate upwards. So I just wanted to give you an idea of what the motion is. And it does, again, it does have a direction. This starts at 0, and the graph that is done here is on the interval 0 to 4 pi in terms of the time. And I just kind of plotted some points at the beginning, and then I connected a nice smooth curve. So I found out where it was at t equals 0, pi over 2, pi, 3 pi over 2, and 2 pi, and I picked those values because those are easy values to look at a sine curve. Okay, so let's kind of go through the rest of this worksheet. So what is the speed of the particle at 2 seconds? So kind of at 2 seconds, it's kind of hard to think about where you're located here because 5 times sine of 2 isn't some nice value. You're at a y value of 1, but it doesn't really matter in this case. We know that speed is the magnitude of the velocity vector. The magnitude of the velocity vector is the Pythagorean theorem of the horizontal velocity and the vertical velocity. Okay, so take and find dy dx and dy dt, square them and use the Pythagorean theorem. So what we're saying here is we're going to take the square root of, again, let's go up here and find dx dt and dy dt. So what is dy dt? Well, dy dt is the time derivative of y. So dy dt is just half t. And then what's dx dt? Right, that's the horizontal velocity. That's just 5 cosine t. So we want to find the speed at 2. We want dx dt at 2 squared. So that's just 5 cosine of 2 squared. Plus plugging in 2 here is just 1 squared. So that's just 1 squared. And then we square those, add them together, take the square root, and we get a speed of 2.31. Let's add that over here. 2.31. And let's say that's in like meters per second or something, or feet per second, some sort of rate. Okay, so what's the distance traveled? Okay, and I actually have that exact same interval graphed here. So I'm literally looking for the arc length here. Or if you are a runner and you started here and you did this in 4 pi seconds, so like 12.5 seconds or something, how far did you go? Remember, the distance is the accumulation of speed. So integrate from 0 to 4 pi of the speed over that time period. So dx dt squared plus dy dt squared. And again, the speed is a function of time. It's changing because the speed at 0 and the speed at 1 and the speed at 2 are all different. But that's what this integral does. So go ahead and plug this in on your calculator. Math 9, integrate from 0 to 4 pi. And then again, you're taking the square root of 5 cosine t squared plus 1/2 of t squared dt. And then go ahead and let your calculator do all the work. And we're going to get 60.32, and that would be in meters. It's the distance you would run along that curve from 0 to 4 pi. Okay, so we want to find dy dx. These next two questions are in the abstract. They don't say find dx at a point, or the second derivative of y with respect to x at a point. They just say what is dy dx. So we know that dy dx, we find it by just looking at dy dt over dx dt, right? It's the ratio of those two velocity components. And so dy dt is just 1/2 t over dx dt, which is 5 cosine t. Certainly you can simplify that, but that is dy dx. Now if you wanted to know dy dx at a point in space, like let's say you wanted to know dy dx at, oh, I don't know, how about pi over 2? At t equals pi over to 2, well, you plug that in, and you plug in 1/2 times pi over to 2, and cosine of pi over 2 is 0, and you're like, huh, I get some infinite slope here, right? This is pi over 4 dividing by 0, let's say it's 0 plus. We get infinity, and of course it's an infinite slope. Where are you at this value? Well, you're here. What direction are you traveling at that moment? Completely vertical, and that's what this slope would mean. So we can find the slope at any moment, and this is just a nice one just to kind of show and remind you that what a vertical line would look like there. And again, that's what a vertical, that's what an infinite slope would be, and that's what dy dx is. Okay, how about the second derivative of y with respect to x? Well, how do you find it? Remember, you take the time derivative of dy dx, so we need the time derivative of this, 1/2 t over 5 cosine t divided by dx dt. Okay, this is kind of gross here because this is going to be a quotient rule, and it's just going to get kind of messy here. So the quotient rule, again, this is the time derivative of this thing, which is dy dx, and dy dx happens to be a quotient. So there's no real way around it. So quotient rule says the denominator, 5 cosine t times the derivative of the numerator, 1/2, minus the numerator times the derivative of the denominator, which is negative sine t, all over the denominator squared. So that's, what, 25 cosine t, all divided by dx dt. And what is dx dt? Dx dt is right here, 5 cosine t. Now this thing is a nasty thing. I mean, maybe we could make this 125 cosine cubed, but either way, if we wanted to find it, we would use the calculator to plug in and find the second derivative at a specific time. So I'm just going to leave it as is right here. I'm not going to simplify that algebraically. Okay, the acceleration vector. So the acceleration vector is just the second derivative of x with respect to time and the second derivative of y with respect to time. Okay, so what is that? Well, that's just the derivative of this. We'll do dx dt, this. So that's negative 5 sine t, comma, the derivative of that is just 1/2. And in this case, we're specifically looking at the acceleration vector at a specific time. So just kind of plug 2 pi into here. Sine of 2 pi is 0, so this just equals, specifically at that time, 0, comma, 1/2. And again, what are those values? That's the horizontal acceleration at that moment and the vertical acceleration at that moment. Okay, let's look at, does the particle ever stop moving? Okay, so what does stop moving mean? Well, if you're going to be stopped, that means that dx dt is equal to 0 and dy dt is equal to 0. Both of them have to be 0. Because if both of them are not 0, then you're at least moving in one direction or not. So you have to decide, are these ever both 0? And in this case, the only way that dy dt is 0 is at 0, and dx dt is 5 at t equals 0. So right away, now dx dt is going to be 0 a whole bunch of times. Right? Cosine is going to go back and forth, back and forth. This is going to have a whole bunch of zeros. So your horizontal velocity is 0 a bunch. Right? Your horizontal velocity is 0 a bunch. But your vertical velocity is only 0 at t equals 0. But when t equals 0, making this 0, this is not. So there's never going to be a time when both of them are 0. Okay, so we can say never in this particular problem. Okay, it's never stopping gonna move. Okay, it has a horizontal maybe of 0 when we're turning around and turning around and turning around, but the vertical velocity at those moments isn't 0. Okay, is it ever moving parallel to the y-axis? Well, what does it mean to move parallel to the y-axis? Well, that would be moving in that direction. Well, what does that mean? Well, that means that dx dt would need to be 0, and dy dt, in this case, would need to be positive, some positive number. So is that ever true? Well, yeah, we already found a bunch of those cases, all of these cases. Anytime dx dt is 0, we're moving parallel to that. Dx dt is going to equal 0 when 0 equals 5 cosine of t, and so we're going to get pi over 2 plus or minus k pi. All of those times the horizontal velocity is equal to 0, which means we're going vertically because we know that dy dt is always positive when t is positive. And if t would be negative, well then we would just be moving down. Okay? Okay, what is the direction of the particle? Now I'm not in love with this, it's a little vague. Are you looking for the slope or are you looking for the angle? And I'm going to give you both. Remember, if I tell you the slope of something, if I told you the slope was 3, I'm pretty much telling you the direction because I'm telling you that this is 3 and this is 1. But with those, then you could find the angle. Okay, this is just a random example I'm making up. So I'll be more specific later on when I say the direction. I mean, what is the angle you're moving? And so in our case, and in any case, all we have to do at 2 seconds is we need to find out the horizontal velocity, which is dx dt, and the vertical velocity, and we just have to find that angle. Okay, well that angle is just inverse tangent of that value. Okay, inverse tangent of dy dx. And why dy dx? Well, what is dy dx? Well, dy dx is the ratio of those two things. Look back on how we found dy dx. It's the ratio of vertical velocity to horizontal velocity. Okay, so if you plug that in, you're going to get, and again, this would be in radian mode, you're going to get a negative 0.448. And the hard part about inverse tangent is you're not exactly sure where it's defined. Remember, tangent is going to be negative in this quadrant and in this quadrant, positive in these quadrants. And so when you do inverse tangent and it's positive, it's always going to give you this value, and it's negative, it's going to give you this value. So how do we know what angle it is? Well, you have to think about what is dy dt and dx dt that made this negative. Which one was negative? Because remember, dy dx is this ratio. And if we look at those, it's going to turn out that at 2 seconds, the vertical velocity is equal to 1, and the horizontal velocity, oh, do I have that written down? I think it might be 2.08, but the idea is that it's a negative 2.08. So I for sure know I'm moving up and left, and so this angle is actually in the third quadrant, and it's this angle. And if we transfer that to degrees, it's going to be 25.7 degrees, and we would say above the negative x-axis. Okay, so that's the direction it's moving. The slope is that ratio, which again, it's basically saying the same thing, and again, it has a negative slope because it's going that direction. Okay, so we'd say it's like north of west, or we can say it's above the negative x-axis. Okay, so that's kind of that first set of problems, and I'll go through the second set now, and the second set is a little bit different in that it gives us dy dt and dx dt as kind of a given. Okay, and so the first one, we had the actual functions. Now we have the velocity vector at the beginning. So let's find the distance traveled, and that question isn't any different than the first one. The distance traveled is going to be the accumulation distance traveled during the first 3 seconds. So integrate from 0 to 3 of the speed. Now I'll write this down. The speed is going to be 3t squared plus e to the t squared dt. Again, if you accumulate speed at every single moment in time and sum those up, then you're going to get the speed, or you're going to get the total distance. The total distance is going to be like 33.34, and let's say it's meters. Okay, find the equation of the tangent line. If I want a tangent line, I know I need an x value, a y value, and the slope. Okay, so let's find the x and the y value first. And like, oh, that's actually just given to us here. We know that x of 1 is -4, and y of 1 is 3. And if we didn't know those, then we would have to do some more work, but that'll kind of be what C and D accomplish down here. So I know the point, and now I need to know the slope. But the slope is just dy dx. And I know how to do that. I just take the ratio of dy dt over dx dt at that moment of 1. And when you plug in 1, you get e to the first over 3, which is just 130. And then all of a sudden I can write the equation of the tangent line. The tangent line and then is just going to be y minus 3 equals 130, right? 130 is the slope, times x minus 4, so x plus 4. And I'm not going to simplify that just because, you know, it's just going to get a little messy. But that's the equation of the tangent line. Okay, so let's do some of the harder ones. Find the x coordinate when t is 5. Okay, so what I want to do is I want to find x of 5. Like, how do you find where you're located horizontally at 5 seconds? Well, I know where I am at x of 1, so I could use that. X of 1 is -4, but I can add what I did horizontally from 1 to 5 by integrating dx dt over time. Again, think about what you're doing here. You're accumulating horizontal velocity. This value is just a delta x. If you tell me where you are at 1, and then you tell me what you did from 1 to 5, I can tell you where you're located at 5. Okay? And when you do this, you end up getting 120. Again, starting value at 1 second, add the displacement from 1 to 5, then tells you where you are at 5 seconds. All right, this next one's going to be a little harder because you want to know where you're located at y equals 0. And you know where you are at y equals to 1. But you can just subtract what you did from 0 to 1 of dy dt dt. Now remember, what does this represent? This represents delta y. That's what you did from the second, from t equals 0 to t equals to 1. But if you want to know where you are in the past, you can just subtract that difference. This is where you're located at 1 second, minus what you did should take you back in time to where you were. And of course, you could just add flipping the bounds as well. And again, that's going to take you back in time. And so when you do that, you're going to get a y value at 0 equal to 4 minus e. And again, you can do these integrals analytically because they're not too bad. Okay? All right, let's do this next one. Find the time when the particle first reaches the speed of 10. Okay, so we want to set the speed equal to 10. So 10 equals the speed. Well, what is the speed? Well, the speed is 3t squared plus e to the t squared. That's the speed function. Again, it's a function because it's changing. It's a function of time. It's different at different time spots. And we want to say, when is it equal to 10? And so you're just solving this algebraically. You would graph this and find the intersection, and you'd get a time of 1.67. Okay, that's not too bad. How about find the time when the tangent line has a slope of 6? Okay, so how do you find the equation? Or, no, we don't need the equation. We just need the slope. What's the slope of the tangent line? Well, the tangent line, that's just, we're saying, when does dy dx equals to 6? Well, dy dx is dy dt over dx dt. And we're saying, when is that equal to 6? Again, we're done now. This is just an equation. We can graph this and find that time. And in this case, there are actually 3 separate times. At t equals 0.2697, -0.212, and 6.7. All three of those times, the tangent line has a slope of 6. Now, I would say most of the time on the test, I will define time as greater or equal to 0. And I also will say find the times, plural, if I want you to find more than one. Okay, so don't be upset if you just found this first one and you kind of moved on. It'll be fine. So on the test, I'll either say find the times, and I certainly will define the domain if I only want you to look when t is greater than 0. Okay, and the last one, it says find the time when the particle crosses the y-axis. So what is the y-axis? Well, the y-axis, if you cross it, you must have an x value of 0. So we're figuring out when can x equal 0. So if you think about x of t for us, well, we know information about x of 1, and then we can figure out a future time by accumulating horizontal velocity. Okay, so think about what this is saying. I want a future position. I'm going to start at 1, and then I'm going to accumulate horizontal velocity over time to get a horizontal change and add that to my original horizontal position to get my final horizontal position. Kind of makes sense. So what do we want to do? Well, we just want to set the final position equal to 0. We know x of 1 is -4. And then we're going to integrate from 1 to some t value of dx dt, but dx dt is just 3t squared dt. And then we can do that integral. Okay, I'm going to come up here. So 0 equals -4 plus the integral. The integral of 3t squared is t cubed, but we need to evaluate that from 1 to some time. Again, this is a definite integral. We need to evaluate this. Okay, so that's 0 equals -4. And to evaluate a definite integral, you plug in the top limit. Right, plugging in the top limit, we're going to get t cubed. And then subtract plugging in the bottom limit. Plugging in 1 cubed is 1. Okay, so these brackets represent me plugging into the definite integral. Well, then I just have to solve this. So this is just -4, -5, throw it to the other side. We get 5 equals t cubed, and we found the time. It's the cube root of 5. And we actually found it exact. Okay, we know that at that time, this accumulation is 4, but if this accumulation is 4 and we started at -4, then we actually got all the way back to an x value of 0, which means we're crossing the y-axis. Okay, hopefully these kind of examples help, but again, look over them again. I ask all the typical questions: distance, tangent line, second derivatives, x and y coordinates, find times when you reach a certain speed or a time when you have a certain slope. The second example was looking at dx dt and dy dt as the given. And if you look at the first example, all of these first questions were all about looking, the given was y and x. Again, I gave you the position functions, but the very first thing we did was still find dx dt and dy dt, and then we kind of just went through some similar problems. Okay, I hope this helps.